Hello everybody, welcome to yet another video by JFB, and in this video we'll be looking at logic gates. This is the second topic in our course. The first topic was about number systems and all that, but I think you got a brief understanding of what that is. Now, what are logic gates? Wait, before I even tell you what logic gates are, I'm gonna ask you a simple question. Have you ever wondered how a computer is able to carry out calculations like 1 plus 1, which is equal to 2, or 2 times 1, which is also equal to 2? Have you ever wondered how a computer is able to carry out big calculations with big numbers? Well, I'm here to tell you that all this simple math, big math, is carried out by logic gates. Now, let's answer what a logic gate is. I want you not to stress yourself and think that, no, a logic gate is something that's big or what. I'm here to tell you that you can think of it as simply a gate. I'll draw some sort of a gate here. I'll draw this gate. This is like a gate. It's an open gate right here. This is a gate and this is a road. So the gate is open right now. It's open. Now I'm here to tell you that a logic gate is some sort of a gate which closes and opens based on what's coming through it. Simply. It's like a gate which will only open up to certain VIPs or certain members of the group and that to allow them passage through. That's how you can think of it. That's the simplistic view. Now let's dive into a little bit more logic. A logic gate is a simple circuit which acts as a switch. If you know what electricity is or have taken any sort of physics course or maybe even the science you took when you were young, a circuit is simply a flow of electricity inside wires. That's how you can think of it. Then a switch is something that can either be on or off, like your bedroom switch. That's it. So the whole logic gate is just a circuit which acts as a switch. So the entire circuit is acting as a switch. So that circuit can either be on or that circuit can be off. So that switch will control maybe a bigger machine and it will either be on or off. Now, why is a circuit acting as a switch so important to computer science? Now, here's where the catch is. Logic. Let's break down what logic is. Logic means something that's understanding or meaningful. That's what it is. So now, this simple on or off by a logic gate mean something actually. They mean something. And for a logic gate to be on, it only goes on when the inputs match some sort of criteria on which it's built. What are those inputs? So since I've said it's a circuit, like at the circuit I said the electricity is flowing through, so you can simply think of the electricity as the input. So electricity is the input. What is the output? And I'm here to tell you again that the output is electricity itself. That's the output. So electricity is acting as both the input and the output at the same time. And what is off? Off is simply when there is no electricity flowing through. So a logic gate is on when electricity is flowing through completely without any harm or anything else, and it's off when there is no electricity flowing through. So now let's try to represent these on and off using other types of values. So I'll say when a logic gate is on, it's 1, and when a logic gate is off, it's 0. If you watched the previous videos, you know where I'm going with. A computer only uses binary bits or binary digits in short, and those binary digits are simply ones and zeros. So the 1 is representing the on, the 0 is representing the off for the entire logic. And this same 1 can represent the inputs, this same 1 can represent the outputs. That's what it is. So now I want you to memorize this or simply understand this or simply just master it, as I now will show you an example of a simple circuit which is acting as a logic gate. Imagine we have this circuit with a battery and some wires. Then these wires are connected to a bulb. I'll simply represent that bulb with some wavy lines like this. That's the symbol for a resistor. So I'll represent that bulb with some wavy lines. Don't get confused. This is just a bulb. Just imagine this is a bulb. So now we represent that bulb with some wavy lines. So now what's happening here? The battery is connected to a bulb. And what will happen to that bulb? The bulb will simply be on. So we can say the on is the 1. There is nothing else controlling this bulb. There is nothing else. Now let's try to introduce some logic to the bulb. How can we introduce that logic to the bulb? We can use a simple switch. And this is how we represent a switch in circuitry diagrams. So some sort of a switch. Now, where can we place this switch without tampering the circuit that much so that we can control the bulb, whether the bulb will be on or off? Well, I'm thinking of one place. What about if we short circuit this circuit? Whereby we just place a wire here and there. So we place a wire here and there. Then we place our switch. So there's the switch. What will happen to this circuit if I close this switch? Well, the flow of electricity will now be short-circuited and the bulb will go off. That's all, nothing else. If I open this switch, whereby the switch is just open, it's like off, electricity will be free and will flow to the bulb, but the bulb will be on. Nothing else will change. So what logic can we get from this? Let's try to map the switch. Let's concentrate on this switch because the switch is actually the thing that's acting as a logic. Let me draw some sort of a diagram. Don't worry, don't be confused. Just a two-box diagram. And let's say we map what's here to maybe an A and what's here a B. So we can say this is an A and this is a B. What do I mean by mapping? When we close the switch, let's say that it's on, the switch is on, and we will represent that as a 1. When we turn off the switch, like it's open, like how I've seen it here, it's 0, it's off. So we're representing the off as a 0 and the on as a 1. Now, I'll place a 1 here. So when I place a 1 and the switch is closed, that means the switch is on. What's happening to the bulb? The bulb has no electricity going through it because the circuit has been short circuit, so it's off. And how can we present that off? With a 0. What if I turn off the switch? The switch, when I turn it off, electricity will flow to the bulb and the bulb will be 1 because electricity is going through it and the bulb will be on. Now you're probably wondering, whoa, isn't that just like what's going on with this circuit? That's what's going on with this circuit, but I'm here to tell you that that's what your computer is actually using to carry out those 1 plus 1. This simple logic. When the switch is on, the bulb is off. When the switch is off, the bulb is on. So in short, there's some sort of an inversion which is going on here. This switch here is acting as a logic gate because it's inverting what's happened to the bulb. When it's on, the bulb is off. When it's off, the bulb is on. So it's inverting the current. Just think of it as an inverter. It's doing some kind of inversion. So like whereby you have a number like 5 raised to power negative 1. This is an inverse. So it's doing an inverse and this becomes a 1 over 5. That's some sort of way it's doing all these things. So it's just inverting 1 over 5. That. Now let me show you an example of real life logic gates and those which are working in your computer. There are many types of logic gates which are working in your computer, but let me show you an example. And before I even show you that example, let me state this fact, which is very important for you to understand. So a logic gate can have multiple inputs. Master this. A logic gate can have multiple inputs, but it will always produce a single logical output. What do I mean by logical? That output has meaning to it. That output is based on what the inputs were. That's simply what it means. There's some sort of outputs which don't even depend on what the input was. It will just be an output like that. So this output for the logic gate is logical. It depends on the input completely. Now, there are 3 fundamental logic gates. 1 is the NOT gate. 2 is the OR gate. And 3 is the AND gate. These logic gates are the fundamental logic gates which are almost in all computers and smart devices and anything that can carry out a calculation. These guys are there. So NOT, OR, and AND gate. What should you master about the NOT, OR, and AND gate? The NOT gate acts as an inverter. The same way I showed that simple circuit, that's how the NOT gate works. The OR gate is something that acts like, if you give me anything, I'll produce an output. Just give me anything, I'll produce an output. So it takes anything. It's not choosy, it takes anything. And for the AND gate, it's some sort of choosy, but it says, hey, for me to work, you have to give me everything. So for the AND gate to work, you have to give it everything. For the OR gate, you just have to give it some sort of electrical input and it's on. For the NOT gate, you don't even have to give it any electrical input and it's on. Isn't that magic? No, it's not magic. It's simply short-circuiting a circuit or it's using some sort of a transistor. Let me not go into those deep things. But just master this. The NOT gate acts as an inverter. It wants nothing and it will work. For the OR gate, it wants anything and it will work. For the AND gate, it wants everything and it will work. So I'll show you how these things work in the next video, where we can dive deeper into the NOT gate, OR gate, and AND gate, and I'll show you how everything works. I just wanted to give you a brief introduction to what logic gates are and what the word even logic gate means. So logic gates depends on the input to produce an output. That's all. So I'll see you in the next one.